Hello and welcome to a Reigate Maths video focusing on the mechanics for the second year of the A-Level Maths Edexcel syllabus. This is Simon, and in this video we are focusing on the topic of hinges. So this is building upon a lot of these similar ideas from resolving forces and friction kind of thing, but they work in a very different way. So what are we talking about when we're talking about a hinge question? Well, the main difference between these and some of the questions that we've done in previous videos, it's what's going on here. So we've got, in this example, we've got a sine of weight 400 newtons connected to a uniform rod of weight 600 newtons and length 4 meters. The rod is connected to the wall by a hinge, and this is the important bit. It's connected, which means it's fixed to the wall. It can still turn, like this end can turn, but this end will not slip. Okay, so there's not going to be kind of a friction here like we had before. You need to find the tension in the cable and the force of the hinge on the rod. So in terms of the dimensions of this, just here, this is 3 meters. I forgot to write it down here, but it's 3 meters. This is 4 meters, which means that because this is at a right angle, this is 5 meters. Okay, knowing your Pythagorean triangles is very, very useful. Here we've got our angle, which we will just call theta for now. We've got our sine, which we're told has weight 400. And we've got the weight of the rod, 600, and that's 2 meters. And we know that there is some tension here. So labeling the forces is all well and good, but then this is the bit that students find typically very difficult about hinges, is what's going on here. So a lot of people will go, okay, well the reaction force is definitely going this way. But the problem is, if this wasn't fixed, this end would want to slip one way or the other. So we would have a friction. Because it's fixed, there's kind of a force maybe pushing up from the rod onto the hinge. So there is a force going in that direction as well. Now the reaction force, or the resultant force that we're going to find, so therefore is going to go kind of vaguely in this direction. So I'm going to call this Rx and Ry. You can give them whatever names you like. As long as it's clear that one's horizontal, one's vertical. You might want to call them RH and RV, or just X and Y. Anything's fine. So once you've got kind of this idea, the questions work very, very similarly to the ladder type questions that we did in a previous video. We're going to take moments about the hinge, so that we can work out the tension, and then we're going to resolve forces so that we can find these, and then eventually find this force R that's acting on the rod. With these two forces, I've put them this way round, which is fine, but if you drew them the other way, that would also be alright. All that would happen is your final value for this would be negative if you put the arrow in the wrong way. So labeling these, as long as you've got one going horizontally and one vertically, the direction doesn't hugely matter. Obviously it does in terms of the physics side of things and the practical and getting it right. But all that's going to happen mathematically, if you put it the wrong way round, is that your answer will come out as minus, which means that your diagram is wrong, and so you need to relabel it. Okay. Finding this force, though, that's not a problem because, well, we've got Pythagoras. So, before we start doing moments, we know we're going to need to do some something with this angle. Conveniently, though, we know that this is a 3, 4, 5 triangle. So this tells us that sine of our angle is 3 over 5. And cos of our angle is 4 over 5. This is going to come in handy later. So we're going to take moments about the hinge. Don't forget, we can take moments about any point we like. We take them about the hinge because it means we don't have to worry about these two forces for this part of the question. So let's look at our forces. So we've only got 3 forces that we really care about. We've got the weight of the rod, which is going to cause a clockwise moment. The weight of the sine, which is likewise going to cause a clockwise moment, and then the tension, which is going to cause an anti-clockwise moment. So let's resolve this force. So we've got our nice triangle. This one's t sine theta, this one's t cos theta. So with kind of resolving your moments, think about, like with forces, think about which moments are going to be bigger, anti-clockwise or clockwise. And you can think about that by going, okay, well, if this sine was going to move, it's stationary, but if it was going to move, which direction would it move in? Well, most likely it would move this way. Because if the string breaks, the sine falls down. We know that. That's what gravity is going to do. So we're going to make the anti-clockwise moments and the clockwise moments sum to 0. Now, I don't like writing them as summing to 0. I like to set them equal to each other. Either's fine. So I'm going to do our clockwise moments. So we've got 600 times the perpendicular distance to our pivot here, so times 2, plus 400 times the perpendicular distance to the pivot, 4. And that's going to be equal to this force here, or the moment caused by this force. So it's going to be t sine theta times by 4. Okay? Because that is the distance, the perpendicular distance from this component of the force to the hinge. So it's just normal moments. This gives us 1,200 plus 1,600, so 2,800, is 4t times, now we've got sine, 3 over 5. So this is 12 over 5t, so therefore t is 1,166.67, so 1,170 newtons to 3 significant figures. So we've now found the tension in the string. When we come back to use our numbers later on for finding the force, so finding this force, we're not going to use this 1,170, we'll use the exact value that we worked out. Okay, so just to keep that nice and, or as accurate as we can all the way through. So now we're going to find the force of the hinge on the rod. So we're going to resolve forces vertically. Okay, which is going to give us that Ry plus t sine theta is equal to 600 plus 400. So Ry plus t sine theta is equal to 600 plus 400. Okay. So Ry is 1,000 minus this times sine alpha, which is 3 over 5. Which then eventually, whoops, that's 1,000, which when we work it all out comes out quite nicely to 300. We do the same thing and resolve horizontally. And in this case, we only have two forces, the Rx and this T cos theta here. Okay, so again, we've got 1166.67 times cos theta, which is 4/5, and it gets that the horizontal component of the force is 2,800/3. Okay, we're going to leave it exact just because, well, we're not done yet. So the last thing we need to do is we need to find the resultant force. So the force of the hinge on the rod, which, going back to our diagram, is this one here. And it's just resolving this triangle and doing Pythagoras with the two components that we found. Okay, so we get the resultant force of the hinge on the rod is going to be 300 squared plus 2,800/3 squared, all square rooted, which comes out to 980 newtons. And that's this hinge question done. So hopefully you can see that the majority of the maths that we've done is identical to the ladder type questions from the previous videos. The difficulty with hinge questions is remembering this here, that they have this reaction. We're going to do a couple more examples that do similar things, but it just with forces going in slightly different directions. So here's the diagram for our next example. In this case, we have a uniform rod of mass 10 kilograms connected to the wall by a hinge, and it's being held in equilibrium by a force acting in this direction at 40 degrees to the horizontal. So looking at this, the big difference with this example and what we just did is looking here. First off, these are given to us. Okay, we're going to call this point A and this point B. How do we know the force here that we're interested in is going in this direction? Well, if we look at the system, there are only two forces that have a horizontal component, X and P. The rod is in equilibrium, so it means it's not moving. So the force here must balance the force going in this direction. So that's why it's into the wall and not out of it. But again, if you did draw it, and if you were figuring these out for yourself and you drew it going that way, all that would happen is your value of X in your working would come out as negative. So you haven't lost anything. So what we're going to do is we are going to calculate the magnitudes of P, X and Y, find the magnitude of the reaction at the hinge, and the angle of the line of action the force makes with the wall. Okay, so very similar to what we were just doing. So, likewise, we're going to take moments about the hinge. In this case, we're told it's called point A, so we're taking moments about A. This is the sort of shorthand notation for that. So, again, let's think about our forces. We only have two that we need to worry about. This 10G and then the P. And this one we need to resolve into two components, P sine 40 and P cos 40. So we can see the P sine 40 is going to cause a turning this way, and the 10G is going to cause a turning this way. So we know they're equal to each other. Oops, 10G times 2 and P sine 40 times 4. Now I know, so this is what sometimes confuses students, I know I drew the P sine 40 starting here, but the force P starts here. So it's got to be where the actual force starts. Okay, not where you've put the component floating. So here we get 20G, it's going to be 4P sine 40, So we can find P very quickly. And we end up with P as 76.2 newtons to 3 significant figures. Now don't forget, because G is correct to two significant figures, 1 decimal place, you can get away with doing your rounding for this question to 2 significant figures. I never would. I would always give it to 3, because that's what you're told on the front of your exam paper. Okay? Unless you're told otherwise, keeping the degree of accuracy as 3 significant figures is a good rule of thumb. So now we're going to do as we did. We're going to resolve horizontally and vertically. So we've got that x is going to be P cos 40, which is this 76.2 times cos 40. Now, because 76.2 isn't exact, I'm going to use the whole number that comes up on my calculator. Actually, I'm going to use this to tidy it up, which I'm aware is 5g tan 40 if you want to, cot 40 if you want to be particularly fancy about it, but let's not. That's entirely unnecessary. Okay, we got there. We're going to resolve vertically, and we get that y plus P sine 40 is going to be 10g. Okay, so resolving forces, we now get that y is 10g minus P sine 40, which comes out as 49 newtons. Now this one does come out exact, because if you look, P is this, the sine 40s cancel, this is just 5g, 10g minus 5g is 5g, 49 newtons. So now what we're going to do is we found the values of P, X and Y. What we're going to do is we're going to find the magnitude of the resultant force and the angle it makes with the wall. So looking here, the resultant force is going to be in this direction, and the angle we're interested in is that. But again, finding the magnitude is exactly the same as what we just did. Okay, 49 squared plus 58.4 squared, all square rooted. Again, we'll use the exact one in our calculator for this, but we'll write this down like that. And this comes out as 76.2 newtons, which interestingly is the same as P. Which means you can probably guess what this angle's going to be. So what this angle's going to be. Okay. Regardless, we're going to have our resultant force here. We've got our y and our x, and this is the angle we're trying to find. So the angle tan theta is going to be opposite over adjacent. So this 58.4 and a bunch of other numbers over 49. So therefore theta equals 50 degrees with the wall. So again, very similar processes. This is just an application of finding forces. The last example we're going to look at is more complicated, but it's kind of, if you can get your head around that, then it is as difficult as it gets. So here's our final example. We now have a uniform boom with weight 700 newtons and an object hanging from it weighing 400 newtons, so 40 kilograms-ish. It could be a light, it could be a boom mic, or something like that. The boom is supported by a light cable and by a hinge at the wall. The first thing we're going to do is calculate T, the tension in the cable, and the magnitude of the reaction at the hinge, so very, very typical. So let's continue labeling some forces. So we can think about the forces at the hinge. So we've got reaction force going up, which again I'm going to call Ry, and a reaction force this way, which I'm going to call Rx. Again, you can call them X and Y if you prefer. The difficulty with this question is that everything's at different angles. So instead of resolving forces, for this one, I'm going to resolve distances. I'm going to do those in a different colour so it's clear. Because don't forget, we want the perpendicular distance from the tension to the hinge. If we can see here in our right angle triangle, this angle here is not just 45, so we've got to really pay attention. We know from our Z angles that this is 20 degrees, so this whole thing is going to be 65. The other thing that's difficult is that we're not told the length of the boom. So that, in terms of a question, that will tell us either one of two things. Either that's something we're going to work out in the question, or the length of the boom doesn't actually matter, so we can give it a name. So the first thing we're going to do is we're going to give the length of the boom a name. So because it's uniform, we know that this 700 newtons is in the middle. So instead of calling the length of the boom, say, A, we're going to call it 2A so we can avoid using fractions. So we can assume the boom is 2A meters in length. So that means this is A and that's A. Which here means that this distance is 2A sine 65. Which is going to be the important one that we need. Okay, so the other thing as well, because these two weights aren't perpendicular to the plane, we're going to need to resolve those as well. Okay, now because of the way these works, that's 20 degrees, that's 20 degrees. So we can get very easily that this force here is 700 cos 20. And this one is 400 cos 20. Once you've got that, this question is now pretty much exactly the same as what we were doing. We'll take moments about the hinge. To find T, then resolve forces to find R. So if you pause the video now and have a go yourself, you can come back and we'll show our working. So taking moments about the hinge, we can see we've got the two clockwise moments caused by the weights and the anti-clockwise moments caused by the tension. Calculating the moments there, simplifying, so we get 700 cos 20 plus 800 cos 20 with some A's in. And then 2A t sine 65. Rearranging to find t, we can see the a's are going to cancel, and we get 1500 cos 20 over 2 sine 65, which we just stick in our calculator and work out. So the thing when we're finding our resolving our forces that we need to be careful of is we need to look back at here. So for the moments, we were always taking it in reference to the plane, so to the rod. But when we're resolving forces, we want up and down, left and right. So we need to make sure that when we resolve tension, we resolve it into horizontal and vertical components, not perpendicular and parallel to the rod. You can do, but then you've got to do a lot more work, and you'll get the same answer. So we can see here, resolving horizontally, we get Rx is T cos 45, which comes out as 550 newtons to three significant figures. Ry is the sum of the weights minus the upward tension, which is 550 to 3 significant figures. And so we get R as 778, which is exactly the same as T, which is interesting in terms of the way this question works. So what follow-up questions could we have? Well, in this example, we assumed the string or the cable was light. You might have to explain how modelling the cable as light affects the model, and you'd say something along the lines of the weight of the cable is not considered, and it's not included in the model. Okay, might be why is it important that the cable is taut, that kind of thing, or why the rod is uniform, or how did you use the assumption the rod is uniform in your calculations? So the centre of mass acts in the middle. So all the assumption type questions that you're used to seeing with forces and that kind of thing can come up again in these questions. But that's kind of it in terms of, if you can get your head around this example here, this is probably as difficult as it can get. Even if you've got sort of planks resting on cylindrical supports or on balls or that kind of thing, you still apply everything the same way. Okay, even though you know if you rest a plank on a ball it's probably going to roll, might not. And you just got to assume that you're taking a snapshot, you're taking a photograph of what's going on. But otherwise, thank you for watching.